Hi girls, today we are going to see about dual nature of radiation and matter. And here the radiation and matter, when you see, they are having dual nature. That means sometimes the radiation will behave as matter and matter will behave as radiation, and that we shall see today. And here when you see the introduction, here we are having particles and waves in our everyday experience. For particles you can take balls, grains of sand, atoms and electrons, and for waves you can take sea waves, ripples in pond, sound waves and light waves. So when you see what is a particle is a tiny concentration of matter. That is when you see sand is a tiny concentration of matter. When you consider the wave, it is a broad distribution of energy and there is no particular place in space for this wave. So it is not localized in space and time, and they both have energy and momentum. So the matter and radiation, they are two forms in the space. And here when you see the electromagnetic radiations, already we have studied about this, and they exhibit a phenomenon such as interference, diffraction and polarization. And whereas when you consider the other phenomena like black body radiation means sometimes that is a black body will absorb and emit. This is called black body radiation. And photoelectric effect, electromagnetic radiations, these phenomena, they behave as particles. So the interference, diffraction, polarization is a property of wave, whereas these photoelectric effect and electromagnetic radiations, they are the property of particles. So when electrons, protons and other particles are discovered, they are only considered as particles. However, in certain conditions they exhibit wave-like properties. So the electrons, protons and other particles, though they are particles, sometimes they exhibit the wave nature, and so this is called a wave particle duality of radiation and matter. So sometimes the electrons and protons, they behave as waves and sometimes they behave as particles, and this is a main part in this chapter. And next we are going to see about electron emission. So when you see the electrons are tightly bound to the atoms, so they are because of the positive nature of the nucleus. So even at a room temperature, there are number of free electrons which are moving inside the metal in a random manner, but they cannot come out because they are strongly attracted by the positive nuclei of the metal. So when you give the attractive pull, this will not allow the free electrons to leave the metallic surface at room temperature. So at room temperature, the free electrons are tightly bound to the nucleus. So suppose if the electrons have to come out, they need energy, and this energy, it is called surface barrier. That is a potential barrier which prevents free electrons from leaving the metallic surface is called surface barrier. That is, we need some energy for the electrons to leave the metallic surface, and so they have to break this surface barrier. So the barrier means some form of resistance. So we have to apply some energy for the electrons to leave the surface, and this is called surface barrier. And so whenever some additional energy is given to the free electrons, they will have sufficient energy to cross the surface barrier. So this liberation of electrons from any surface of a substance is called electron emission. And so the electrons are emitted if you give some energy. And what is work function? Next we shall see. Work function is the minimum energy needed for an electron to escape from the metal surface is called work function. That is, we are providing some energy, and this minimum energy which is given for the escape of electrons is called minimum energy, and this is measured in electron volt, and this is a unit for work function. And so when you see here, next there is one example given. Suppose if we take the maximum kinetic energy of the electron is 0.5 eV and the surface barrier is 3 eV. That is, we have to overcome this 3 eV, and for that we have to give the energy for and this energy is found out by subtracting both of them. that is 3 minus 0.5, which is given as 2.5 eV. This 2.5 eV is called work function of the metal. So we have to supply this energy for the emission of electrons. And so here if the smaller work function, the electron emission is more effective, because extra energy required to release the free electrons from the metal surface is smaller. That means we need only a little amount of energy for the electron emission. So smaller the work function, effective will be the electron emission. And so here there is one tabular column given, which give you we are having some metals with their work function. And here there are 4 types of electron emission. We shall see one by one. The first one is called thermionic emission, and from the name itself we can find out that the emission is that is induced by giving temperature. So it is called thermionic emission. So here sufficient energy in the form of thermal energy, so that they are emitted from the metal surface, and so this is called thermionic emission. And this diagram shows you about this. And so the electrons are, in the first diagram, the electrons are bounded to the nucleus of the metal, whereas in the second diagram we are giving some thermal energy, so the electrons gain the energy and they are liberated. This is the second diagram. And so here the examples are cathode ray tubes, electron microscope, X-ray tubes. These devices, they use thermionic emission for the emission of electrons. And next, so this is the diagram which shows you about the filament of cathode ray tube. Here you are having the filament and it is heated by the battery. So because of this heat, the electrons are emitted. And next, field emission, that is we are going to give a strong field which pulls the free electrons and helps to overcome the surface barrier, and this is called field emission. And the examples are electron microscope and field emission display, etc. And here when you see the diagram, in the center you are having the metal with free electrons, and a strong electric field is applied, and because of this the electrons are emitted, and it depends upon the value of the energy we are giving. The next emission is photoelectric emission, and photo means light. So when light falls on certain materials, the electrons are emitted, and this is called photoelectric emission. So the energy is transferred from the radiation to the free electrons. And so what is this? The number of electrons emitted depends upon the intensity of the incident radiation. So here this is called photoelectric emission, that is when an electromagnetic radiation of suitable frequency is incident on the surface of the metal, the energy is transferred from the radiation to the free electrons. So the free electrons will get sufficient energy to cross the surface barrier, and the photoelectric emission takes place. And the examples are photodiodes, photoelectric cells, etc. And here when you see the diagram, and here the radiation is falling on the metal surface, so the electrons will gain the energy and they are emitted. And the fourth one is secondary emission. In this, when you see this diagram, you can understand high speed electrons are falling on the metal, and this will give some energy to the free electrons, and so the electrons which are gained energy are liberated from the metal surface, and the emitted electrons are called as secondary electrons. And the examples are image intensifiers, photomultiplier tubes, etc. And so here these are the 4 types of emission of electrons from the metal surface, that is we can trigger the emission of electrons by these 4 ways. And the next important concept is photoelectric effect, and already I have told you photo means light. So when light falls on certain materials, electrons are emitted. This is the concept of photoelectric effect. And Hertz, Hallwalk and Lenard, they showed about the photoelectric effect by doing the experiments. And here we have already studied about electromagnetic waves. So Maxwell is the first one who predicted the existence of electromagnetic waves, and light is also an electromagnetic wave, that is concluded by him. And Hertz is the first scientist who produced experimentally the electromagnetic wave, and the experiment we have seen in the chapter 5. And here when you see the induction coil, and the red dot shows the spheres, and in between the spheres, when high voltage is applied, get ionized, and so the spark is produced, and this spark will oscillate back and forth and they produce electromagnetic waves. This is called Hertz experiment, which we have studied this in the 5th chapter. And so here the main problem in this is how to detect the tiny spark that is produced. And here you see in between the spheres there is a tiny spark, and there is a very large problem in detecting this tiny spark. And later Hertz made many attempts to detect the spark, and then finally he came out with a solution, that is, when they are exposed to ultraviolet light they become more vigorous. So when ultraviolet light is incident on a metallic spheres, the electrons on the outer surface are emitted and cause the spark to become more vigorous. And so in this way he detected the sparks that are produced in between the metallic spheres. And next we are going to see about Hallmark's observation. In this we are going to see about the strange behavior of the spark due to the action of ultraviolet light with this simple experiment. And there are 3 diagrams given in this. In the first one, the zinc plate is kept and gold leaf electroscope, and this gold leaf electroscope apparatus is connected with a zinc plate, and first the zinc plate is positively charged, and in the next case, that is, it is uncharged, and here in the next case it is negatively charged, and in the third case it is positively charged. So when you see, if an uncharged zinc rod is exposed to ultraviolet rays, the wire will become the plates will become positive, and positive will repel, so the leaf will move away from each other. But when the ultraviolet radiation is falling on a negatively charged plate, then the plate will become more that is, they give out more electrons, and so the leaves now which are separated will come closer now. And when you see the third part of this experiment, here a positively charged zinc plate is exposed to ultraviolet radiation. Here the more electrons are produced, and so the plate will become more positive, and because of that the gold leaf electroscope, the plates will move away because of this more positive charge. And so here this is an experiment which shows that when ultraviolet radiations fall on the zinc plate, electrons are emitted. This is the main part of this experiment. And so here the gold leaf electroscope we have studied in the lower class. It is nothing but a plate. 2 plates are mounted like this, and these plates, when they become positively charged, they will move away from each other, whereas when the charge is leaked out, they will come closer, and when the charge is more, when the positive charge is more, they will move apart. And next we are going to see about Lenard's observation, and here we can see about the electron emission phenomenon in detail. And here when you see this experimental setup, this is a discharge tube, and here one side you are having cathode and other side anode. The cathode is usually the negative plate which is connected with the negative of the battery, and positive is connected with anode with a galvanometer. Galvanometer is used to detect if any flow of current is present in the circuit. And so here the ultraviolet radiation, they fall on the cathode tube, and because of that electrons are produced, and these electrons are accelerated towards the anode, and they induce a current, that is, they give the current, and which is shown by the deflection in the galvanometer. That is a part of this experiment. And so here the current flow is indicated by the deflection in the galvanometer. So from this we can see that when ultraviolet light falls on a negative plate, the electrons are ejected from it, which is attracted by the positive plate. Whereas when you see, when the ultraviolet radiations, they fall on this positive plate, there is no emission of electrons. So only the negative plate will give you the electrons, which are then accelerated towards the anode. And this is the quartz bulb. The experiment is carried out in a quartz bulb, and here so the main concept is ultraviolet light, when falls on the negative plate, the electrons are ejected. So the ultraviolet light falling on negative plate causes electron emission from the surface of the plates, and this phenomenon is called as photoelectric effect. So the photoelectric is a phenomena in which when light falls on certain metals, electrons are emitted. And these electrons are called as photoelectrons, and the current is called as photoelectric current, or simply you can call it as photocurrent. And the metals cadmium, zinc, magnesium, they shows this photoelectric effect. Even some alkali metals such as lithium, sodium and cesium also they respond well to the larger wavelength. So these materials are called as photosensitive materials. That is the materials which eject photoelectrons upon irradiation of electromagnetic wave or suitable wavelength is called photosensitive materials. So the above said metals are called as photosensitive materials. And next we are going to see about the effect of intensity of incident light on photoelectric current. Suppose if you increase the intensity, what happens to the photoelectric current? And usually when the intensity is increased, the current also increases. And this is shown by the experimental setup. And here this is the discharge tube, and here you are having photosensitive plate, either zinc or magnesium or any plate is kept there, and there is one quartz window, and this window will allow the ultraviolet radiation to fall on this photosensitive material. And anode is usually positively charged, and here this arrangement is called as voltage divider arrangement. That is, you are giving a very high potential difference. You have to give a very high potential difference, which is shown by the battery, and PQ is the voltage divider. That means you can give any amount of voltage, also positive or negative, any type of voltage you can give to the anode. And the current is usually measured by using microammeter. Since current is in very small amount, you can measure only by using microammeter. And this voltmeter is connected between the anode and the cathode to show the value of the potential difference that is given to anode and the cathode. So this is an experimental setup, and here when ultraviolet radiation falls on this zinc or any plate through the quartz window, the electrons are ejected. So here the necessary potential difference between C and A is provided by the high tension battery B, which is connected to the potential divider arrangement PQ through a key K. And so you can find out any positive or negative potential to A with the help of this voltmeter, and it is having 0 marking initially, and it can measure either whether the potential is positive or negative. So in first case, if there is no light falling on the cathode, then no photoelectrons are emitted and the microammeter reads 0. Whereas when ultraviolet or visible light is allowed to fall, the photoelectrons are liberated, which are attracted towards the current. And so here now the photoelectric current is set up in the circuit, which is measured by using microammeter. And now we are going to see the variation of current with the intensity, the potential difference, nature of the material, and the frequency of the incident light one by one. And first we are going to see about the effect of intensity of incident light on photoelectric current. And in this, the other two are kept constant, that is the frequency and the accelerating potential V of the anode are kept constant. And here the potential A is positive with respect to C, that I already know. Usually C is given negative potential and A is given positive potential, so that the electrons are attracted towards A. And here the intensity and the corresponding photoelectric current is measured, and the graph is shown here. So from the graph you can understand that when the intensity increases, the current also increases, and here the other two things are kept constant, that is the frequency and accelerating potential. And so you can say now the photo current, that means the number of electrons emitted per second, is directly proportional to the intensity of the incident light, which means that when the intensity increases, the photoelectric current also increases. So this is about the first graph. Next we are going to see about the effect of potential difference on photoelectric current. So you can keep the frequency and intensity constant. So when you study about one variation, the other two things will be kept constant, and here the frequency and the intensity of the incident light are kept constant. Here we can see the potential of A, and when you see the anode is usually given positive, and so when the potential of A is increased, also the corresponding photoelectric current will increase. So it reaches the saturation current, and that will be shown by the graph. When you see here, the electrode potential is given in the x-axis and photoelectric current in the y-axis. So when you increase the potential of anode, actually the current also increases, and the intensities are I1, I2, I3. That is for 3 different intensities you are measuring the photoelectric current. And so here when you increase the anode potential, the photoelectric current also increases, which is given by the straight graph, that is saturation currents. And so this straight line, they represent the saturation currents. And for a particular intensity, suppose if you decrease the anode potential, then the photoelectric current also decreases. This is shown by the left hand side, that is the decrease in the anode potential also decreases the photoelectric current, and even it is made negative. So the left hand side graph represent, that is the anode is given the negative potential. So this is called retarding potential, because the anode is usually given positive potential, but now you are giving the negative potential, so the electrons are not much accelerated towards the anode. So here the photoelectric current decreases and slowly it reaches V0. That is V0 is called the stopping potential, that is where the photoelectric current completely becomes zero. That is electrons from the cathode are not at all reaching the anode. That is electrons are completely stopped near the cathode. So that is called the stopping potential. And whatever may be the intensity, I1, I2, I3, whatever may be the intensity, the stopping potential is same for all the intensities. But when you see the saturation current, for a higher value of intensity, the saturation current is also higher. And so this graph is very, very important. And retarding potential means the potential given, negative potential given to the anode, which makes the electrons to stay near the cathode itself. And so here the stopping potential definition is very, very important. It is the value of the negative potential or retarding potential given to the collecting electrode A, which is just sufficient to stop the most energetic photoelectrons emitted and make the photocurrent zero. So instead of giving positive potential to the anode, here we are giving negative potential, so the electrons are just stopped, and so it is called stopping potential. And so here when you see the maximum kinetic energy, so every electron will have a different type of kinetic energy. So when you take suppose the fastest electron, that means the kinetic energy is maximum, we are going to stop this fastest electron by applying the stopping potential. And so here kinetic energy is maximum. Suppose if we take that is maximum for a particular electron, K max is equal to half mv square maximum, which is equal to E V0. Here V0 is the stopping potential, and you know E is the charge of the electron, and here V max is the maximum speed of the emitted photoelectron. So when using this derivation, that is here the kinetic energy is equated to the stopping potential. And so here V max is equal to square root of 2E V0 by m, by simplifying the equation and substituting E, that is charge of electron, but you don't know the value of V0, that is stopping potential, and you just apply the mass of the electron, you will get the expression as 5.93 into 10 power 5 square root of V0. And kinetic energy is usually given by E V0 if the unit is joule, and kinetic maximum, that is a maximum kinetic energy, is given by V0, and usually the unit is EV, that is electron volt. So you can use any of these equation, that is the two equations are given, either you can use EV0 or simply V0, but when you use EV0 the unit should be in joule, whereas when you use V0 the unit will be in electron volt. And so here when you see the stopping potential, is it independent of the intensity of the incident light. When you see this graph, whatever may be the intensity I1, I2, I3, the stopping potential is a constant, so it is independent. And the maximum kinetic energy is also independent of intensity of the incident light, because the stopping potential is also directly proportional to the maximum kinetic energy. And next topic we are going to see about the effect of frequency of incident light on stopping potential. And already we have studied about stopping potential, that is the amount of negative voltage given to the anode for which the photoelectric current becomes zero is called stopping potential. And we are going to see about the effect of frequency of incident light on the stopping potential. And here the variation of photoelectric current with the collector electrode potential studied for radiations of different frequencies, and you are just varying the frequency and you are finding out what is the amount of current. And so here when you see the same x-axis and y-axis, retarding potential in left side and collecting electrode potential and photocurrent in the y-axis. And so here when the frequencies are different, nu1, nu2, nu3, the stopping potential is also different. And here the frequency when it is lower, the stopping potential is also lower, which shows that when the frequency increases, the stopping potential also increases. So it is a straight line graph. When you see this diagram, the frequency and the stopping potential, they are directly proportional. And so the first graph is for one metal and the second graph is for another metal. Suppose if a frequency is more, then the stopping potential is also more. So here you can say that when the frequency is increased, the photoelectrons are emitted with a greater kinetic energies, so that the retarding potential needed to stop the photoelectrons is also greater, because the kinetic energy is increased by increasing the frequency. And so here from this graph we find out that the stopping potential varies linearly with the frequency, but at a particular frequency there is no, that is below a particular frequency, there is no emission of electrons, and this is called threshold frequency. That is when you decrease the frequency and below a certain value there is not at all the production of electrons. And this threshold frequency is, the frequency is increased above threshold value, the stopping potential varies linearly with the frequency of the incident light. So to get, that is a minimum value of a frequency is required for emitting the photoelectrons, and this frequency is called threshold frequency. And below this frequency there is no electrons. That is the main point. Below a certain frequency called threshold frequency, no electrons are emitted. And we are going to summarize these points as laws of photoelectric effect, and already we have studied these points, just we are summarizing this. The first one is, for a given frequency of the incident light, the number of photoelectrons emitted is directly proportional to the intensity of the incident light. That is, the frequency is kept constant, and here the intensity will depend upon the photoelectric current will depend upon the intensity. Also, the maximum kinetic energy of the photoelectrons is independent of the intensity of the incident light, because the kinetic energy will depend only on the frequency. That is the next point. The maximum kinetic energy of the photoelectrons from a given metal is directly proportional to frequency. So kinetic energy is independent of intensity, but it is proportional to frequency. And here next one is, the minimum the emission of photoelectrons will take place only if the frequency is greater than a particular frequency, and this frequency is called threshold frequency. And below this threshold frequency there is no emission of photoelectrons. That is the main point. And there is no time lag between incident of light and ejection of photoelectrons. That is, as soon as the light falls on the metal, the electrons are emitted and there is no time lag. That is, there is no time required for the emission of electrons. And so these are the laws of photoelectric emission. That is 5 points are there. Next we shall see about concept of quantization of energy. And here in this we are going to see about the failures of classical wave theory. That is, a wave theory is a third theory, and this wave theory is not able to explain this photoelectric effect, because according to wave theory the light is propagated in the form of wave, but according to this theory, the photoelectric effect cannot be explained. And we shall see how the failure take place. And here, according to wave theory, light of greater intensity should impart greater kinetic energy to the liberated electron. But we see that the kinetic energy will depend upon only the frequency and not about the intensity. So here, this is the first failure of the wave theory. That is, according to wave theory, the light of greater intensity should impart greater kinetic energy to the liberated electron, but the intensity of light is nothing but the energy delivered per unit area per unit time. And already we know that the maximum kinetic energy does not depend upon the intensity of the incident light. And next, according to the next point, the electrons will be liberated. It is whatever may be the frequency, the electrons may be ejected. But lower the frequency, the electrons will not be liberated. So this is failed to explain the existence of threshold frequency. That is, threshold frequency means a minimum frequency required for the emission of photoelectrons. So the wave theory couldn't explain this threshold frequency. Also, according to this wave theory, the energy of the light is spread across a wavefront. That is, it is a continuous form of energy, but it is not like that. So, suppose if it is a continuous form of energy, it will take some time to liberate, but the electron needs considerable, the electrons will emit immediately after the ultraviolet light is falling on the metal plate. So, here it is an instantaneous process, that is, a time lag is less than 10 power minus 9 seconds. Within this time, the photoelectrons will be liberated. So, this property is not explained by wave theory. So, the photoelectric emission could not be explained on the basis of wave theory of light. So, the wave theory of light couldn't explain the photoelectric emission. So, only the particle nature of light can explain this photoelectric effect. And so, we are going to see about particle nature of light, because the wave theory couldn't explain the photoelectric effect. So we shall see now the particle nature of light. And here, when you see here, the light is electromagnetic wave, and sometimes it is acting as a stream of quanta. That is, it is a stream of particles which is having energy and momentum. The energy is given by the formula E is equal to h nu, and the momentum is given by P is equal to h nu by C, where h nu is the energy and C is the velocity of light, and P momentum. So sometimes the light will act as a stream of particle or a stream having small packets of energy, and these small packets of energy is called as quanta, and this packet is having energy E is equal to h nu and momentum P is equal to h nu by C. So photon is nothing but particle manifestation of light. That is, light in the form of particle, it is called as photon. Next we are going to see about the characteristics of photons. So photons are nothing but light of frequency nu and wavelength lambda, and they have energy E is equal to h nu. And nu is a frequency, and that can be replaced by C by lambda, where C is the velocity of light and lambda is the wavelength. So here the intensity is no relation with the energy, because there is no intensity in the formula. So the intensity has no relation with the energy. And so the momentum is given by the formula P is equal to h by lambda, or substituting for lambda you can write h nu by C. So the photons are electrically neutral. So they don't have positive or negative charge. So they are unaffected by electric and magnetic fields. And photon interacts with matter. That is, they will react with photon electron. So it is called as photon electron collision. And photon may be absorbed or new photon may be produced. So only the energy and momentum is conserved, whereas the number of photons may not be conserved. So these are the characteristics of the photons. So photon is nothing but a light particle. And next, Einstein's explanation of photoelectric equation. So when energy of photon h nu is falling on a metal surface, it is completely absorbed by a single electron, and the electron is ejected. So we can see this diagram, and here the energy E is equal to h nu is falling on the metal, and the electron is ejected. So the energy that is falling on the metal surface is used in two ways. One, it is used to liberate the electron, and the other, it is used to impart the kinetic energy. And so the total energy is used in two ways. H nu is equal to phi naught plus half mv square. This phi naught is nothing but work function. That is the minimum amount of energy required to release the electron, and half mv square is nothing but kinetic energy. So this is very important equation. H nu is equal to phi naught plus half mv square. And so here suppose if the energy E is equal to H nu naught, where nu naught is the threshold frequency, that is very less amount of frequency, then the kinetic energy almost becomes zero, because below the threshold frequency the emission of electrons is not possible, and nu is a frequency, nu naught is a threshold frequency. And so in such a case, if we reduce the frequency of the incident radiation, the speed or kinetic energy of the photoelectrons is also reduced, and it almost becomes, kinetic energy becomes zero if the frequency is equal to threshold frequency. So you can substitute that in the equation. So here H nu is equal to phi naught plus half mv square. The half mv square becomes zero. So you know H nu is equal to phi naught, and phi naught is nothing but the work function. Substituting this in the equation phi naught, you will get H nu is equal to H nu naught plus half mv square. This is called as Einstein's photoelectric equation. And here nu naught is threshold frequency, and half mv square is the kinetic energy. If there is no loss in any because of collisions, then maximum kinetic energy is equal to half mv square maximum, where Vmax is the maximum velocity of the electron ejected. So the kinetic maximum in this equation, the kinetic energy half mv square will become H nu minus H naught. And so here kinetic maximum is equal to H nu minus phi naught, where phi naught is called the work function. So there are different forms of photoelectric equation. There are three forms in Einstein's photoelectric equation. And when you see this diagram, you are drawing a graph between frequency and the maximum kinetic energy. When the frequency increases, the kinetic energy also increases, and below this frequency there is no emission of photoelectrons. And so this is the y-intercept. Y-intercept means in the y-axis it reaches at a particular place, and this value is called as H nu naught. And so here the slope of the line is usually called as H, and its y-intercept is minus phi naught. And you know phi naught is the work function. So we are going to find out the slope is independent of the metals. Suppose when you see this diagram, we are having calcium, sodium, potassium, cesium, etc. The slope remains constant. Whatever may be the type of metal, the slope H is always a constant, but H nu naught will vary. That is, the energy will vary. And this is the concluded by Millikan. And Millikan calculated the value of Planck's constant, that is 6.626 into 10 power minus 34 joule second. And also he had calculated the work function of many metals, that is cesium and sodium, potassium and calcium. So for these metals he found out the work function, and you know the work function is the minimum amount of energy required to release the electron. And next we are going to see about the explanation of photoelectric effect on the basis of that is photoelectric theory. So based on Einstein's photoelectric equation. And so here already you know this point. When the intensity increases, the number of electrons also increases, thereby increasing the photocurrent. And the kinetic maximum is directly proportional to the frequency of the incident light, and is independent of the intensity of the light, because in this equation there is only frequency and no intensity. So the maximum kinetic energy will depend upon only the frequency and not about the intensity. And here below the certain value of frequency there is no photoelectron, and this minimum frequency is called the threshold frequency. And this is very important point. There exists a minimum frequency called threshold frequency, below which there is no photoelectric emission. So there is no also time lag between incidence of photons and ejection of electrons. As soon as the photons fall on the metals, electrons are emitted. So the photoelectric effect is well explained on the basis of quantum concept of light, and the wave nature of light cannot explain the photoelectric effect. And next we are going to see about the nature of light, that is wave particle duality. Duality means it exhibits a two type of character. Sometimes it behave as wave and sometimes it behave as particle. So light is having dual nature, and during interference, diffraction and polarization they behave as waves, whereas in black body radiation photoelectric effect it behave as particle. So sometimes light behave as wave, sometimes light will behave as a particle. And so this is the main point in this. So it is therefore concluded that light possesses dual nature, that of both a particle and wave. It behaves like a wave at some circumstances and it behaves like a particle at some other circumstances. So that's all, girls. Hope you understand this portion.